All right. So we're going to start talking about loudspeakers, specifically directivity of loudspeakers, and we're going to start doing some projects about that. So there's a couple of concepts I want to kind of just introduce to you first, which is that we have learned so far that sound travels naturally. It tends to want to go every direction. It travels equally in all directions, unless otherwise acted upon by some other force to make it not do that. So it wants to travel equally in all directions. And up until now, all of our math about how sound propagates is assuming that it's going everywhere. Okay. All of our math about, okay, how do you calculate how many watts goes into a loudspeaker that generates this much SPL that then hits the audience at this level, that's all assuming that the loudspeaker is sending the sound everywhere equally. But loudspeakers don't do that for a lot of reasons. Some are reasons that we have created for ourselves. We don't want the loudspeakers to go everywhere, to spray the sound everywhere, or we just have to be okay with them not sending it everywhere because it's the way that we've designed the technology imposes some limitations on the way it propagates. So one of the concepts that comes into play, particularly for folks who are maybe designing horns for loudspeakers, is this concept of Directivity Index and Directivity Factor. The idea here is, remember I said that sound naturally wants to go in all directions unless it's acted upon by some other force that's trying to get it to not do that. So there could be lots of things that would make sound not go in every direction. Like say, you could put a horn, a directivity horn, on a driver. You could stick a loudspeaker inside of a box. You could put it inside of a room. That would confine where the sound goes, right, if it hits a bunch of walls. So remember, I've probably said this earlier, that basically all of our technology that we have at our disposal for sound involves making things louder. All right, that is the fundamental paradigm for every bit of technology that we have, is how do I make something louder? Okay, everything we do starts there. How do we make something louder? And directivity is no exception to that. So when we're talking about loudspeaker directivity, we're primarily interested in making the sound louder. And we make it louder by confining it. So instead of all this energy going everywhere, we can take some of that energy, and instead of having the energy go backwards, if we can somehow get it to go the other way, then that area where it is propagating will be louder, because it's got twice as much energy going towards it, because all that stuff that used to be going behind me is now going forward. So the concept of a directivity index is an amount in dB, or decibels, that represents the actual increase in sound pressure level that you get by confining the sound in some way. So if you can somehow confine that sound, get it to not go every direction, then the area that's left where it's propagating will be louder. How much louder? X number of dB. We call that the directivity index. The amount that it got louder because you confined it. Okay, you focused that energy in one direction, and therefore it gets louder. And directivity factor, otherwise known as the Q, like letter Q, is a ratio. So when you see like a Q of 2, that's a ratio. That means it's a ratio of 2 to 1, the 1 being the unconfined sound, and the 2 being the confined sound. So we have a 2 to 1 ratio between unconfined and confined sound in their intensities. So the confined sound is twice as loud as the unconfined sound, which we know would be, if in dB, if you count for comb filtering and stuff, would be a directivity index of 3 dB. Okay? Yeah?
Related to the Q you see on EQs and
That's something different. That's different, but it is a similar concept. I like to think of Q as it is a ratio between two intensities in the context of loudspeakers, but just Q as a thing, whether you're talking about directivity or you're talking about filters, it's talking about confinement. How confined is the sound, or how confined is the filter? So a higher Q in an EQ, in a filter, would mean that that's a very narrow filter, right? It's only affecting a small range of frequencies. So high number means narrow, whereas a low Q would mean it's not confining the filter very much at all. The filter is taking a whole lot of frequencies with it. In the context of a loudspeaker, a very high Q would be a very narrowly controlled loudspeaker. Okay, so the sound is confined extensively into one small place. You know, you could see a Q of 10 to 1, which would be a 10 to 1 ratio in intensity between the unconfined sound and the confined sound. So it would be a Q of 10, which we know, if you count for comb filtering, would be a 10 dB increase, 10 to 1 ratio. Yeah? Because you multiply by 10, you get a 3 dB increase. If you, even in sound pressure level, assuming comb filtering happens, and comb filtering always happens. If it wasn't comb filtered, you'd get a full you'd get either 20 dB at a 10 to 1 ratio, or you would get 6 dB at a 2 to 1 ratio if comb filtering didn't happen. But comb filtering does happen, so you usually only get about a 3 dB increase. So let's take a look at an example here. So one of the ways that sound gets confined is walls. Okay, we tend to put sound inside of rooms. It's not always true. Sometimes we do sound outside. But because of weather, we tend to like to be inside because we can control the climate a little bit. So this is just a diagram. This thing that looks like a sunburst, that's the sound. That's the thing making sound. And it's, you know, the lines represent the sound going every direction. Okay? And then over here on the right, this is representing, you know, a measurement point, which could be like a microphone or a sound pressure level meter or something, some device that measures how loud the sound is. And then we have the L is just length, distance. Okay, so there's a certain distance between the thing making the sound and the thing measuring the sound. Okay? In this case, our directivity index is 0 dB because we are not confining this sound at all. It's going everywhere. No confinement, 0 dB directivity index. Directivity factor is 1, or a Q of 1, because there's a 1-to-1 ratio between confined and unconfined sound, because the sound is not being confined. We have no increase in level. Okay? However, what happens if we try to confine this sound a little bit? We can take that same rate, I would call this the radiator. You'd take this and you could put it up against a wall. And what happens is all of the sound that used to go this way is running into the wall. Right? And what's going to happen to that energy? It's going to go, oh, I can't go that way. I'm going to go the other way instead. Okay? So now you've got twice as much energy over here than you used to. So in that case, now you've got a directivity index of 3 dB because you got a 3 dB increase in sound pressure level because you doubled the amount of energy, and because of comb filtering, it's not a perfect 6. You actually get 3. And in this case, the directivity factor is 2, or a Q of 2, because we have a 2-to-1 ratio between what we had before we had the wall and what we have now with the wall is a 2-to-1 ratio because we've doubled the energy on top of itself. 3 dB increase. Yeah?
Is the plus 3 because of comb filtering, is that like just a, it's probably around plus 3?
It's an average, yeah. It's an average, yeah. Yeah, in a perfect world, it'd be 6. And if this was a subwoofer, it would be 6. Right? Because you get much lower than 100 hertz, and you just can't comb filter that.
Is that why you need less subs than speakers?
Not necessarily. It just means that, you know, you get a lot more bang for your buck if you can figure out how to confine the sound coming out of a subwoofer, which is hard to do because the wavelengths are so large. But if you can figure out how to confine that subwoofer's radiation, then you get a huge increase in level, because comb filtering is not a thing with really low frequencies. I mean, it's possible, but it just requires huge offsets, right? So, all right, we could take this further. If we added another wall into this, so this could be the floor, take the same radiator, put it in the corner on the floor, and now you've got 2 walls, right? So you're folding that sound back onto itself twice. Okay, so before we had half the sound going this way and saying, oh, it can't go that way, I'm going to go this way. And now you got another half the sound going down to the floor and saying, oh, can't go there, I'm going to go back up. So now you're going boom, boom. It's folding on itself twice. You get a 6 dB increase at the measurement point. Yeah?
Does it matter where where it's reading it? Because the way that it looks like is that it looks like it's, since the walls are closing in on it, it looks like it kind of shoots in a diagonal.
That's just because I'm trying to show that it went down there, but the idea is that this distance is the same.
Okay.
And it's the distance that's the important part, right? Because sound decays over distance.
Okay.
So yes, the angle is different, but the distance is staying the same here, okay? So in this case, we get a 6 dB directivity index because we got 3 dB for every wall we added. We added 2 walls and get 3 dB per wall, so now we get a 6 dB increase, and now our directivity factor is 4, or a Q of 4, because it's a 4-to-1 ratio between the unconfined sound and the confined sound. Okay? Because we've doubled it twice. All right, we could take it even further and put it in the corner with 2 walls and the floor. And if we get 3 dB increase per wall, and we have 3 walls now our directivity index is 9 dB. So we have a 9 dB increase in level as a result of putting it into this corner with 3 walls. And now our directivity factor is 8, or a Q of 8, because it's an 8-to-1 ratio between the unconfined and confined sound, because we doubled it 3 times now. From 1 to 2, 2 to 4, 4 to 8. Right? 8-to-1 ratio between confined and unconfined sound. Okay? So here's the cool thing. Remember I said you get 6 dB per wall with subwoofers? So what if you put the subwoofer in the corner? What would be your directivity index? 18 dB. You can get 18 dB more sound out of that subwoofer without turning a single knob if you just put it in the corner. Yes?
Is this why, like, Colby in Seams Resolution is aiming his speakers at the wall? Is that?
No, that's a different thing. No.
That's not the same thing?
This doesn't have anything to do with where you aim it. This is assuming that the thing making the sound is omnidirectional. Okay? And a loudspeaker inside of a box is usually not omnidirectional. Okay? So that's a different thing. That is just an effort to try to make the loudspeaker seem like it's further away. Right? Because if it bounces off the wall and then comes back, that's sort of like it was on the other side of the wall. Yeah. Okay, so so hopefully you kind of get this idea. This is what you have to start thinking about when you start thinking about directivity of loudspeakers, is that yes, they get directional, and that means that you have more sound where you point it, but it also means it's louder, right? It got louder because you confined it. That's why we put loudspeakers inside boxes, because the box confines it. It doesn't let any of that sound come off the back. And all that sound has to now go out the front. So it gets louder when you put it in a box. Okay? So let's take a look at the math here. We're not going to do any of this math because this should be familiar to you by now. But I just want you to see the mathematical relationship between directivity index and Q. So directivity index is 10 times the log of Q. And the Q is 10 to the power of directivity index divided by 10. These should be very familiar formulas to you by now. So if you have Q, you can derive directivity index and vice versa using those mathematical equations.
Why is sound so log heavy? Almost all the equations we do in some way have log in it.
Well, because of the range of sensitivity. So, our hearing the sensitivity of our hearing is huge. That amount of pressure ranges from 1 to a trillion. Those are just really big numbers. And when you get to, our ability to hear the difference between 500 billion pascals and 501 billion pascals, we can't hear that. So our ears just don't have that resolution. Even though we had this huge range of sensitivity, it's a very low resolution within that range. So logarithms correspond much more closely to how we hear, and we use them everywhere. We use them in the context of calculating loudness. We also use it in the context of looking at frequency response. If you look at most frequency response graphs, whether it's in SoundGym or in an EQ or something, you notice that is not a linear progression on that as you go up the frequencies. Those frequencies, as you go up to higher and higher and higher, you're taking huge chunks with you. It collapses because that's how we hear it, all right? It's easy for us to hear the difference between 100 hertz and 110 hertz. It's not so easy to hear the difference between 5,000 hertz and 5,010 hertz. Very difficult for us to hear that difference, okay? So the logarithm scale corresponds much more closely to the way that we hear, okay? And it also makes the math easier because we're dealing with smaller numbers as opposed to enormous numbers, which we would normally have to deal with. Okay, so there's been a lot of efforts in trying to figure out how do we plot and communicate directivity, because ultimately there's a lot of work and science that goes into trying to figure out how to get loudspeakers to send the sound where you want it and keep it out of the areas where you don't want it. So there's a lot of work that goes into that, and most of the reason that you would pick one loudspeaker over another is not because of its loudness, right? Because that's what we've been talking about so far is, okay, how loud is it at this distance? And yes, that's important, but that's usually not why you choose it. It's easy to find a loudspeaker that will get as loud as you want. It's more about which one will disperse the sound the way I want it. Because I want the sound to be, in the case of theater, live sound, we tend to want the sound to go to where the seats are and nowhere else. We don't want the sound to go to the stage. We don't want it to go to the walls. We want it to go to the audience seats without going anywhere else. So how do you figure out, how do you look at a loudspeaker and figure out where's the sound going to go when I turn this thing on? So one way that that can be represented is polar plots, okay? And the idea of a polar plot is, we are looking at, this is probably a horizontal polar plot. So you're looking, down at the top of the loudspeaker here. And what we're saying is, at 0 degrees, this is where you're pointing the loudspeaker. So if you had like a laser on the front of the loudspeaker and you moved it, 0 degrees is like, where is the laser dot? It's pointed at Ryan, okay? And there's this circular grid here, okay? And each of these thin lines in circles in the grid represents usually a certain dB decrease. Sometimes that's 5 dB per division, 6 dB per division, 3 dB per division. Usually it'll say, and I just cropped it out of this one, but there will be a little note that says 3 dB per division, or 5 dB per division, or 6 dB per division. This one is probably 3 dB per division, just based on what it looks like it's doing, okay? So what that means is the solid dark line here, that is the loudness of the loudspeaker. So if at 0 degrees you're at this line, that's your reference point, okay? And what they're saying here is when you go to 60 degrees off axis horizontally, the sound coming out of that loudspeaker now intersects with the second thin line, which is 3 dB quieter. So here is minus 3 dB. Here is 0 dB, okay? Then you go to 90 degrees, and notice how this dark line is now intersecting here. We've now gone 1, 2 divisions. So now this is minus 6 dB. See that? We go down here to 150 degrees. Now we're minus 9 dB. See how that works? So at 180, there's a little bit of it balloons out just ever so slightly. It's probably closer to 8 dB there, minus 8. Okay, you see how that works? So this is cool. It's easy to read this. It's easy to get a sense of, okay, the people sitting 90 degrees off axis of this thing horizontally are going to hear something 6 dB quieter. Yeah?
Is this what you use when you don't have access
So ease is something different. So what you got to realize is that technology that allows you to plot that, digitally in three-dimensional space, that didn't exist when we started doing research into loudspeaker directivity. Like, you couldn't do that. So a lot of these plots I'm going to show you were ways people trying to figure out, how do I do this on a piece of paper, right? But yes, what ease is trying to do is plot directivity. It's just utilizing it in a different way because it can plot all three axes at the same time. And that's the problem with a polar plot, for example, is you can only look at one axis at a time. So this is just horizontal axis. But of course we know that there's, if I took the loudspeaker here and I sliced it in half, that'd be the horizontal axis. And you could also do a vertical axis. But this 45-degree angle axis would be another directivity you could look at, and vice versa. So there's, the sound goes everywhere. So trying to do that all with polar plots would require a lot of polar plots, right? Only one polar plot per axis and per frequency. Because one thing you'll find about loudspeaker directivity is not every frequency disperses the same way. Some frequencies will disperse very narrowly, and some frequencies will disperse very widely in each loudspeaker. So a polar plot, while it's very easy to read this, it's not a very efficient way to document the loudspeaker directivity, because to use only polar plots to show you what the loudspeaker is doing, you would have to have a whole lot of them. So you'd have to have one for every axis and every frequency that you cared about. And I'll share with you on Friday some polar plots, some actual documents from loudspeaker manufacturers that have polar plots, and it's page after page after page of polar plots. It's like, okay, 250 hertz horizontal, 500 hertz horizontal, 1 kilohertz horizontal, and so on and so forth. And then you do the whole thing again for vertical, it's just like page after page after page of these things. So easy to read, but not particularly efficient. However, you'll still see this from time to time. If you look into specifications and documents about loudspeakers, they might still show you a polar plot here and there. Every once in a while, you'll see that they will try to plot more than one line on each graph, and they'll separate. Each line will be a different color, or one will be dashed, and that's their effort to try to show more than one frequency at a time. So a different color would be a different frequency. Yeah?
Why don't they just make a list of at 30 degrees we lose like 3 dB or something?
Well, you could, but this is just, the nice thing about this is you can kind of look at it and get a sense horizontally how wide does it disperse before it decays. And trying to, peel that out of a big spreadsheet would be really difficult.
Like on the websites, like if you go to the JF80 manual, they'll have like 12 of these right next to you.
Yeah.
Through all of it. So it's kind of like, it's not like you have to go and search for everything.
So let me show you, I think I've got an example of what you're talking about. Let me see if I've got it here somewhere. I might have to find it. I don't see it here. So maybe on Friday I'll show you what that looks like, what you're asking about. I thought I had it, but I don't. But and it's awful, right? It's just like an insane amount of numbers that are thrown at you. You can't possibly make sense out of it. Okay, so let's look at another one. This is called a beamwidth plot. And the concept behind a beamwidth plot is that, remember we've talked about decibel values and okay, what is the minimum that people can hear? What did I say? What is the smallest change in decibel that an average person can perceive? About 3 dB, right? Much less than 3 dB, and your average person is going to feel like, you didn't really do anything. Now, with training, that you can get to where you can kind of hear a 1 dB difference, much less than a 1 dB difference, and it's really, really hard to hear that. I mean, yeah, you can kind of barely maybe perceive that something happened, but unless someone told you that they changed it, you wouldn't know that it changed, right? Okay, so 3 dB is the smallest amount that a human can hear. Yeah.
Question on that while we're on it. For me, when listening, for doing that stuff on sound chip, it is easier to hear differences when the overall level is higher. So if it's louder, it's easier to hear a difference than if it's quieter.
Well, so that gets into the logarithmic nature of your hearing, right? So you notice that faders are like that. That, you know, when you're down at the bottom range of the fader, that half a centimeter difference is, you're making a huge change, as opposed to that same half a centimeter at the top of the fader is a smaller change. So there's a lot in play there. One of them is the resolution of hearing, but the other is the noise environment that you're in. So you know, if the sound you're listening to is closer in level to the noise floor of the room that you're in, then you're going to have a harder time separating the thing you're listening to the noise that you're not listening to. But you should still try to get good at hearing it at lower levels, because the amount of difference is the same, whether it's loud or quiet. The difference is the same. So you should still be able to perceive it. Now, the amount of actual pressure that changed is vastly different. Okay? If you measured the actual number of pascals of pressure that changed at that high level versus the low level for that same 3 dB change, it's different. Okay? But the way you perceive it is the same. Okay? However, the concept of the beamwidth plot says that, okay, if 3 dB is the smallest amount of change that anyone could really perceive on the average person, then we've kind of made a rule of thumb in professional sound that says we're willing to tolerate deviations in level, give or take 3 dB. Right? So we call that plus or minus 3 dB. So we can tolerate, if we're talking about directivity and frequency response, when someone says it's a flat frequency response, what they usually mean is it's flat plus or minus 3 dB. Because once anything gets more than 3 dB different from something else, even an average person could hear that. Now so if it's plus or minus 3 dB, that's a range of 6 dB. Okay? So in the context of loudspeakers, we're willing to tolerate the sound decaying as much as 6 dB before we feel like, okay, that's too much. If there is one person that's hearing more than 6 dB quieter of a show than another person, then that's a range we tend to not be comfortable with. But we're kind of okay with, the difference between the person sitting in the center and the person sitting over to the right. If the person on the right is hearing 6 dB quieter of a show, that's okay. Okay, because that's not enough for them to feel like it was significantly quieter. If 3 dB is what they could barely perceive, 6 dB is like, okay, that would be okay. But much more than that, we were not real happy with. So what this thing shows is what is the beam width for 6 dB down. So there's a 6 dB down point on either side. So on axis, I point the loudspeaker at Ryan. How far to either side do I go before it gets 6 dB quieter? Okay? And we call that the beam width, because that's the usable range of the loudspeaker. Because I could point this anywhere, but as long as the audience is within that range, that 6 dB down on either side, then I'm okay. So this is showing you beam width per frequency at both horizontal and vertical axes. So for example, here at 1 kilohertz, vertical, we are 90, 80, 70, 60 degrees. So this particular loudspeaker at 1 kilohertz has a 60-degree beam width on the vertical axis, which means you go 30 degrees up or 30 degrees down and you hit 6 dB quieter. Okay? But on the horizontal axis, it's like 85. So this is 60 degrees, 85 degrees on the horizontal. So it's much wider on the horizontal than it is on the vertical. But another thing to note here is that beam width, that we could, you could probably round that to 90. That 90 by 60 is not consistent. It doesn't do that for every frequency. You see that? You get down here to 100 hertz, and it is effectively omnidirectional on both axes. Whereas up here at, 2, 3, 4 kilohertz, it's probably closer to 70 degrees on the horizontal. You see that? So that beam width is a moving target per frequency. And so that's kind of what's nice about the beam width plot, is you kind of get a sense of how controlled the loudspeaker is. The sort of holy grail for, for loudspeakers in a live reinforcement setting is that all the frequencies disperse at the same angle. Right? You would want that would be the perfect scenario, is when you say this loudspeaker is a 90-degree horizontal by 40-degree vertical, that's at every frequency. Right? That would be the perfect situation, but that's just not achievable.
Do you think it'll ever be achievable?
I don't think so. Because we've been trying. We've gotten pretty close now, actually, with a few really interesting tricks. That's kind of what line arrays are trying to do, is try to get that to be more consistent, but it's super expensive to pull that off. And even that is not perfect. Yeah.
Two things. If that's what the beam width looks like when they're saying, is it 70 degrees horizontal, what is 70 degrees horizontal?
Exactly.
Do they just pick one? Or is it usually like everybody does 1K is 70, or is that not standardized?
Everybody does a little bit differently. I'll say that some people will just pick a frequency. Like, generally speaking, 1K is the point of no return. It's like, on average, it's difficult to expect that you could control frequencies lower than 1 kilohertz. So most people sort of pick up that beam width and say, all right, what does it do at 1K? And that's what we'll publish, because that's where you can start getting control over it. But then, of course, it gets much narrower at higher frequencies. So then what some people will do is they'll just kind of take an average of this. So they'll sample all these values, and they'll just say, okay, well, generally, it's hovering around those lines, right? And even though it's give or take, it's narrower, and then they'll publish whatever that average is. But yeah, that is a significant observation, because you look at a spec sheet and it says, oh, it's a 90 by 40. That doesn't mean anything, because it's not doing that at every frequency. At best, it's doing it for all frequencies 1K and above. And everything below 1K is effectively omnidirectional. So, but even above 1K, it can't be doing that perfectly consistently. So, yes, it's far more complicated than marketing people would care to let us believe.
So is that just because, I'm looking at the JF80
Yeah.
spec sheet right now, and the response of it is pretty flat. Like, every frequency is pretty much being made at the same level from 100 to 10K.
That's on axis, though.
The beam width is completely
Yeah.
like that.
So that frequency response is on axis. That's if you're pointed straight at it, and directivity hasn't become a thing yet.
Okay. Yeah.
Right? So, all right. So this is one way of looking at it. The nice thing about this is it gives you a good sense of when this thing starts crapping out on you. And you can kind of see, okay, it's kind of more or less controlled until you get to 1K. Maybe 1500. But after that, it just goes, it just stops being able to control the sound. Okay, another way of looking at this is called the directivity plot. You tend to see this in the context of horns. If you're going to buy like a horn to go into a cabinet, you're going to stick it to a compression driver. They're going to plot a directivity plot of the horn. And what you have here is on the right, you have directivity factor, or Q, between 1 and 1,000. And then on the left, you have directivity index in dB between 0 and 30. And then frequency response on the horizontal axis. So it's really just plotting Q and directivity index per frequency. And again, what you can see is for this is actually a pretty good looking horn, right? It's really consistent from about 1500 hertz to 10 kilohertz. That's a really good horn. You don't see that very often. But, you know, after that 1500 hertz, omnidirectional. Okay? Another way of looking at this is what's called an isobar.
What do you see?
That's right. That's right. It's like an ink blot test or something, right? So you've got what this is trying to show you is the 6 dB down, 6 and 12 dB down points per frequency. So you're probably looking at, this might be the vertical coverage. So you're saying, you know, if this is 0 degrees, you know, then you're going 10 degrees, 20 degrees, right? Plus 10 degrees, plus 20 degrees, and eventually you hit this line. That's 6 dB down point. And so the next line is 12 dB down. So presumably everything in this gray area is somewhere between 6 and 12 dB down. You don't really know what, that doesn't have that resolution. But you just kind of want to know per frequency. It's another way of looking at that beamwidth plot. It's a very similar concept to the beamwidth plot. It's just plotting it a little bit differently. So here again, with this one, you can kind of see that it's pretty well controlled, 4K to 10K or so. And then it kind of opens up a little bit between 1K and 4K. And then it narrows again right there at 500 hertz. This is, by the way, this is a D&B Q7. So this is that narrowing at 500 hertz is where those two dipole drivers kick in, and they start canceling out on one axis, and that thing narrows in. Okay, just another way of looking at it. But here you're really seeing, here's the 6 dB down point, here's the 12 dB down point. Okay, here is getting to kind of your observation, Ryan, about frequency response, is that one way, you know, yes, loudspeakers get quieter when you move off axis of them, but more accurately, their frequency response changes. Because as we know, not each frequency has a different directivity. So what really happens is when you move off axis of a loudspeaker, its frequency response changes. Some frequencies get quieter and some don't, depending on which ones are directional and which ones aren't. So what this thing shows you is, this is called a family of off-axis frequency response curves. So you're showing the frequency response of the loudspeaker per degree off-axis. So the solid line is the on-axis frequency response if you're right in front of it. And then if you move 10 degrees off-axis, then this next line kicks in. I'll use the thing. Okay, so that dotted line now comes into play. And you go 30 degrees off axis, and now you're at this line. So the frequency response is changing. So part of the other thing that we mean when we say, oh, well, we're comfortable going 6 dB down on either side, it's because within that range of that beam width of 6 dB on either side, the frequency response is more or less consistent. Overall, yes, the loudspeaker is getting quieter, but the frequencies are decaying consistently. And past that 6 dB down point, the frequency response is changing too dramatically for us to be okay with it. So you can kind of see in this one that the frequency response stays pretty consistent to this 20 degree point, right? I mean, all these frequencies are getting quieter. You can't really expect, you know, the lower frequencies to do this. But, you know, from 2K and above or so, it's decaying consistently, right? This frequency response is pretty similar to that frequency response. It's just a little bit quieter. But then you get down here to 30 degrees, and that frequency response is fluctuating more than it used to. So I would hazard a bet that this loudspeaker is probably spec'd at a 40 degree beam width for this axis. 20 degrees on either side, because once you get past that 20 degrees, the frequency response is changing too dramatically. It starts sounding vastly different. Okay? So that's another way of looking at it. Okay. Here's another thing you can think about. Why is it that loudspeakers aren't consistent in the way they disperse the sound? Why can't, when we say it's a 40-degree beam width, why can't that be for every frequency? And it has to do with the way we've designed the technology. So most of our loudspeaker technology involves what we would call circular radiators. So they are loudspeakers that are circles. And you have circles pushing and pulling on the air. And what we find is that circles behave very predictably in the way that they can control that sound. So here is a set of polar plots. We've just kind of sliced them in half to make it a little bit easier to read all of them at one time. And this is the same loudspeaker driver. Now this is no box, no cabinet, no anything, no confinement, just a round or circular driver hanging in the air. And you put sound through it. Well, what you notice is that its ability to control frequencies is different for each frequency. And it has to do with the relationship between the diameter of that driver and the wavelength of the frequency it's trying to produce. So if the wavelength of that frequency is larger than the diameter, it's basically omnidirectional. So that driver cannot be directional over a frequency whose wavelength is larger than the driver itself. Just can't do it. And it's not until you get here where it's now trying to produce a frequency whose wavelength is the same as the diameter of the driver. Okay? So the diameter is equal to the wavelength of the sound. When that happens, now suddenly that driver can be directional. It can exercise control over it. And if you were to plot this full thing, it would actually look like this. So it becomes kind of a figure-8 pattern. And those of you that knew Brett last year, this was what he was playing around with a lot. He was trying to get that to happen at all frequencies, that kind of figure-8 pattern, and see if he could use that to his advantage. But that happens at the frequency whose wavelength is the same as the diameter of the driver. And that's the take-home message here, is that any loudspeaker, I don't care what it is or what it's made of, it cannot be directional over frequencies that are larger than the physical size of that driver. Yeah?
So I thought this whole time that the reason we had 18-inch subs was because they had better directivity at lower frequencies. But 30 hertz is drastically larger than 18 inches. So what is the point of having an 18-inch sub?
So yeah, it's mostly about amplitude, right? So we need we know that our sensitivity is less for lower frequencies. So that larger diaphragm can just push more air, right? It's able to push more air, and therefore it can do it at a higher amplitude. Sort of. But yes, it's also can be kind of directional over some things. But usually for subs, even an 18-inch sub, what frequency has a wavelength of 18 inches? No. Yeah, exactly. I mean, that's like in the 500 hertz range, okay? So yeah, that's not why. Okay? And then, so what you see then is now as you go up the scale, as the wavelengths get narrower, if the wavelength of this frequency is smaller than the diameter of the driver, it starts beaming that sound, right? Narrower and narrower. Okay, so you get to this range where the loudspeaker is 6 times larger than the wavelength, and it's like a laser beam, right? I mean, it is shooting that sound just only at the thing you're pointing it at and nowhere else, because it can be super directional over that frequency. Now, here is the really important part of this. There's 2 things that are really important. One is that you can knowing this, you should be able to look at any loudspeaker without even looking up at specifications or anything. So this one that's up in the air over here on the right, you should be able to look at that and you can tell me right away what frequency it can be, what's the lowest frequency it can be directional over. Looks like it's about 8 inches diameter, that low driver. So what frequency has a wavelength of 8 inches? Well, 1 kilohertz is 1 foot, right? 2 kilohertz would be 6 inches, so it's probably around 1,500 hertz or so. So it's just physically not possible for that loudspeaker to be directional over anything lower than 1,500 hertz. It's not possible. Physics does not allow it. Okay? So that's one thing that you can understand, is if you know this concept, you can look at any loudspeaker you want, and you can get a sense of how directional it's going to be, at least down to its lowest frequency. The other thing is this helps you understand why we put more than one driver in a loudspeaker. Okay? So a common misconception is that, well, the smaller drivers can better, they can produce the high frequencies, and the bigger drivers can produce the low frequencies. And the big drivers just can't produce those high frequencies, and the smaller ones can't produce the low frequencies. That's not true. Not true at all. Think about that for just a second, and you'll realize that that's not true, right? So, every time you have ever stuck, a little earbud in your ear, you have a single driver producing all of the audible frequencies, and it sounds just fine, right? So a driver this big can produce all the frequencies, okay? It's not that it can't produce it. It can. They can produce all of them. It's just that it can't produce them at the same directivity, okay? So that little teeny earbud is not going to be able to be directional over anything. It's too small, right? Even the highest frequencies are larger than that little earbud, okay? But it doesn't matter because it's pointed straight into your eardrum. You're always perfectly on axis to that thing. So even though the high frequencies are beaming like this and the low frequencies are going everywhere, you're hearing them all flat because you're all perfectly on axis to them. Yeah?
All right. Musical instrument question.
Okay.
I've played with switching out different speakers, whether a 10-inch, 12-inch, 18-inch, and I noticed a tonal difference between those. Does that have less to do with the size of the driver and more with the other components, such as the magnet?
It has to do with directivity.
Okay.
Because that's the only difference.
Okay.
Again, assuming that all the other components are the same, the only thing that's different is the size of the driver.
Yeah.
Those larger drivers are just going to be more directional down to lower frequencies.
That's interesting.
So they're going to be more controlled. Okay? So the real reason that we put multiple drivers into loudspeakers is to try to control the directivity and get it to be consistent. Because we know that the diameter of the driver has to be equal to the wavelength of that frequency in order for it to be directional at all. So if we can put multiple drivers in there of different sizes and somehow divide the frequencies so that each driver is only reproducing frequencies whose wavelengths are similar in size to that driver, then we can get the whole thing together to produce a somewhat consistent directivity. You got a question?
No.
Okay. So, for example, let's just figure this out. So, three-way loudspeaker, yeah? So let's say that this is 12 inches. Okay? This one is 6 inches. This one is 3 inches. Okay? What frequency would this low driver be directional over? 1 kilohertz, right? So, okay, it would do this, right? For 1 kilohertz. So I could say 1 kilohertz. And I could do a range of that. I could say this will be, this driver is going to get, oops, let's try that again. Maybe this driver will get 500 hertz to 2,000 hertz-ish. Or maybe just 1,500. That'd be better. 1,500, okay? And it would be fairly directional over those frequencies, okay? This one, 6 inches. What's it going to be directional over? The other way. 2 kilohertz. 2 kilohertz has a wavelength of 6 inches. So this one would be, this 6-inch driver would do the same thing at 2 kilohertz that the 12-inch driver does at 1 kilohertz. So this one would get 1,500 to maybe 3,000. Okay? 3-inch driver, what's it going to do? 4 kilohertz, right, is what it would be directional over. So this one will get 3,000 to 5,000 hertz. Okay? Guess what? Between 1,500 hertz and 5 kilohertz, this loudspeaker will be pretty consistent directivity-wise. It will do this for that whole range of frequencies. Right? That's why we put more than one driver in the loudspeaker. It's about directivity. It's not about frequency response. It's about directivity.
When I'm, looking at my loudspeakers for my design, and it's saying that the drivers are, so I'm getting a 6.5-inch driver.
Mm-hmm.
My mid-bass range, and it says that it has frequency response of 50 to 5K, 50 hertz to 5K. What is the, I think Ian was asking this question as I was thinking kind of, but like what is the determining factor of why it's not 50 to 10K?
So usually, so that, first of all, that is on axis.
Yes, because
That's on axis response.
do directional, it's only 6.5 inches.
So when it says that, when it says, oh, it's 50 hertz to 5 kilohertz or whatever, that means on axis. And that means usually plus or minus 3 dB. Okay? So it just means that once you get down past 50 hertz, it's more than 3 dB quieter than 1K or something, right?
So I get the lower frequencies because it's not the way it's designed isn't able to move enough air,
Mm-hmm.
stuff like that. But like with higher frequencies, you'd think that why can't it extend into that range?
So I think this
That's
is
the way it's designed to.
this is not my area of expertise, but it doesn't mean that it doesn't produce that frequency. It can. It's capable of producing 10 kilohertz. It just can't produce it at the same loudness. 10 kilohertz is more than 3 dB quieter than 1 kilohertz, and therefore it drops off that frequency response graph. So, and some of that is just because it has to be like how fast can that mechanism actually move. It's just there's a mechanical limitation there, but it's also just there's a lot of other things that go into that. But that's important to note, though, that just because it says, oh, this thing ranges from, this driver can do 500 hertz to 4 kilohertz, it doesn't mean it can't do 200 hertz. It just means that 200 hertz is more than 3 dB quieter than those other ones, and therefore you can't count it, right? Okay, so let me give you now a graph of what this looks like if you can leverage multiple drivers. So this is one driver, not in a box, just you try to shoot different frequencies into it. This is what it does. This one is this is, I believe, a DMB E0, which we have in our shop. Okay, so first of all, we put it in a box, so it gets a little bit louder. But we also have 2 drivers in here. So an E0 has, I believe, probably like a 4-inch and a 2-inch, or maybe a 4-inch and a 1-inch driver. And then it's divided the frequencies across that. So look what happens now. You don't get that beamy thing that was happening at the really high frequencies. Why? Because by the time we get to these high frequencies, we've switched over to a smaller driver. and the smaller driver can't be as, it's now smaller than the frequencies it's trying to reproduce, and therefore it disperses them more widely. It can't control them the same way. Yeah? More than one driver. And you no longer get the laser beam. Okay? Other questions? So this is really the bread and butter of designing sound systems, okay? So much of it is about directivity. How do you get the sound to go where you want it to go and not where you don't want it to go? Because you don't want it usually to go onto the stage. You don't want it to go onto the walls if you can help it. You want it to go only where the ears are and nowhere else. And you want all the sound to go only where the ears are and nowhere else. So that's the challenge. How do you get all the sound to go where you want it to go and not where you don't want it to go? And how do you get it to sound more or less even frequency response? It's difficult because of some of these limitations that we've discussed. That's the way that we've designed our technology lends itself to these limitations. But now maybe you can start to understand why we do things like line arrays, okay? So one of the things that a line array does is a line array element behaves much more like this first graph than the second one. And so as you add a whole bunch of cabinets to it, as you get higher in frequency, each one of those is getting narrower and narrower, which means they don't interact as much, right? They don't overlap with each other, and therefore they don't comb filter as much as you get higher in frequency. So you can take that and shoot it really far, and these individual drivers are not comb filtering with each other, which means collectively they behave as though they are one larger driver. Okay?
The reason why they are not overlap or interact with them is because of the directivity?
Yes, because they get they do this beamy thing. They get narrower and narrower and narrower. So they're spaced apart such that the extent to which they are directional gets narrower and narrower as you get higher in frequency, and therefore they never overlap in a destructive way. Right? That distance stays consistent. And therefore, you can get a stack of these, and you can line them up and make it 20 feet tall, and it's like you have one 20-foot diameter driver, at least on the vertical axis. Well, what frequency could you be directional over if you had a 20-foot diameter driver? Yeah. Around 50 hertz. And you are, from 50 hertz onwards, consistent, at least on the vertical axis. On the horizontal axis, you're still only, a foot wide, okay? So that's one of the ways we've gotten over this, is that what line array technology allows us to create virtual, enormous drivers out of lots of little ones. So we can be directional down to lower frequencies.
So I get how that's extremely useful when you're throwing the length of a football field.
Yeah.
But what happens when you have the width of a football field and the width of a stadium that you're at?
Yeah. Well,
You just have to have a ton of line arrays?
well, keep in mind that ultra directivity is only on the vertical axis. On the horizontal axis, it's still going everywhere because it's narrow, right? So that one line array goes wider than you think, okay? But at that point, you have to get into stuff we're going to talk about later, which is, okay, how do you create arrays, right? To sort of, okay, I know this one will cover this area, so how do we get another one that picks up where that one left off to cover the other area? So you just end up with horizontal arrays of vertical line arrays. And so, yes, now the other thing that happens is because these individual drivers don't interact destructively, they actually sum constructively. That's why they appear to defy the inverse square law, right? So they decay 3 dB per doubling of distance as opposed to 6 dB, because all the individual drivers, as you get further away, you're hearing more of them, right? If I'm right up against that line array, I might only be hearing one driver. But as I get farther away, now I'm hearing 2 of them. Farther away, now I'm hearing 4 of them, just because my angle relative to each of them is different. So you get farther away, you're hearing more, and they're not interacting destructively. So as it's getting quieter, it's also getting louder because you're hearing more. So 3 dB per doubling of distance, which is why you can shoot it down the length of a football field and not lose as much energy as you would expect. But that's not why you see them used in theater, because in theater, we're not usually shooting very far. So we don't really care about that, but we care a lot about that vertical pattern control down to low frequencies. That's what gets us our game before feedback. So generally speaking, line arrays are not really designed for theater, and they're not used widely. But when you do see them used, when you see, a 10-foot line array hanging up above a theater for a musical in a 800-seat theater, it's not because they're trying to shoot a long distance. It's because they are trying to keep low frequencies off the stage. And the line array helps them do that because the line array is really directional on the vertical axis. So if it's a 10-foot line array, what frequency is it going to be directional over? Around 100 hertz. So it can keep 100 hertz and above off the stage, which is helpful. Yeah?
So, would there be much benefit to us using like the Q1s and making a line array, even though it's only fitting like 3 boxes? Because you got the 2 Q1s and the Q7.
We have 4 Q1s. So you could.
So would you just do one full line array, or would you?
Yeah, that's why we bought them.
Okay.
So you could make a line array that was 4 boxes tall. They're 12 inches tall, each of them. So it'd ultimately be a 4-foot tall line array. So what frequency could you be directional over? 250 hertz. That's way better than 1 kilohertz, right? Which is where you normally can be.
So when you hear feedback, usually it's like a ringing, like higher.
Yeah.
Up there, why would keeping the low frequencies up help that if it's not them that are?
So we'll get into that in a few weeks, but the feedback is happening when the sound from the loudspeaker gets into the same mic that the natural sound does, and so the reason that the low frequencies, well, one frequency feeds back because there's a phase relationship that makes it work there, but the low frequencies tend to feed back first because they're less directional. They're more likely to make it to the stage than the high frequencies are. So to solve feedback, after you've solved the other geometry problems that we'll discuss in a few weeks, it's more about how to get more directivity, because the lower you can get, the more directional you can get to lower frequencies, the less low frequencies hitting the stage. And you know what? Usually you roll off, you do high-pass filters to 100 hertz on all your vocal mics anyway, just because there's not a whole lot happening in the human voice there. And if you've got a line array that's directional to 100 hertz, then you have effectively very little energy hitting the stage, which means you've got gain for days. Okay? Other questions? All right. Yes?
Didn't get why line array has 3 dB.
Yeah. So let me show you. Let me do it this way. Okay, so here you have a loudspeaker, yes? And here you have a person. Okay, so they're hearing that driver, and there's a distance involved here, right? And they will hear a certain number of decibels. Well, when they go here, they've now doubled their distance away. This will be 6 dB quieter. Okay? And now they go here, minus 12. Oops. Right? Now they go here, minus 18. Yeah? That's inverse square law, right? And that's just what that one loudspeaker will do. Okay? However, if I have another one right here, well, this person probably isn't hearing this one very much because it's going over their head. Okay? But if and so would one here, right? So if I had a whole bunch of them, this person isn't hearing that one. But as you get here, this person is probably hearing both, right? So this person is probably getting both of them. This person is getting all those ones. It's probably able to, because the angle is just narrower, right? Whereas this person is hearing all of them, right? And because these don't comb filter, even though this person is hearing minus 18 dB for every single one, every time we doubled the number of cabinets we have, so in fact, to do this better, I would need to have 1, 2, 3, 4, 5, 6. I would need to have 8. Right? So every time I double the number of drivers I'm hearing, I go up 3 dB. Right? So even though I lost 6 dB off of this one driver, I picked up another 3 dB because I heard 2 drivers. So now, for the line array, I'm only minus 3. And here, yes, I lost 12 dB off of this one, but I picked up another 3 dB for the other, for this here in the second driver, and then another 3 dB for hearing 2 more. Because every time I double them, I get another 3 dB. So now I'm at minus 6. Whereas this one, yeah, I'm down 18, but I gained another 3 dB for the other 4 drivers now that I hear. So now I'm only minus 12. Because the farther away you get, you're hearing more loudspeakers. So yes, it doesn't, oops. So it doesn't actually break the inverse square law, because that's not possible. But it appears to. It seems like it doesn't, it breaks that law, because as you get farther away, you're also hearing more loudspeakers. So it gets louder at the same time it gets quieter. Okay? And really, the only advantage that gives you is that it means that to get whatever level you need here, so if that's 100 dB here that you need, hopefully you don't need that much, but if it's 100 dB here, and if inverse square law applied, then you would have to have 118 dB here, okay? But instead, with the line array, you really only have to have 112 dB here. So that it's just overall less sound you have to generate in order to achieve that. So that's why the people in the big stadiums do line arrays. They're not concerned so much about the directivity. They're concerned about not having to generate quite so much sound at the stage in order to be loud 3 football fields away. Okay? Right. Yeah. We're interested in it less because we want to make that much noise. We don't. We're interested in it because we want to keep the sound off the stage. Because all of our people are wearing omnidirectional microphones. We don't have the advantage of a directional microphone on a stand that can be pointed directly off axis to the wedge that's pointed up at the performer. We don't have that luxury. We can't do that. So, because yeah, they don't. The rock and roll guys, they don't care about keeping sound off the stage, because they're shooting sound to the stage, because they have all these monitor wedges going everywhere. So that's not why they do it. They do it because of this. So they can hit 100 dB without having to generate 200 at the stage, right? Yeah? Okay, that's it. So on Friday, we're going to look at how do we use some of those different kinds of plots, like the isobars and the polar plots and stuff, to actually plot loudspeaker coverage into a CAD file. Okay, so how can we look at a CAD drawing of the theater and draw out where the sound will go using that directivity data? Okay?